and then the meter. When I call your name, please make sure that I hear the clear here. Sanjun, Lee, Dawood, Alavi, Rini Song, Yogi Saputra, no one is here. Boxan Zhang, Minglian, Keith McGuinness, thank you. One catch, Sue, one Pin Sue, yes. Rocky L. So this one has only the pen name. You should put your pen name only once and then use your name. Andy Peruca? Here. Thank you. Faisal A. Here. Duanil Chosky? Here. Lee Hong? Here. Thank you. So, but right, because I don't know what they wrote or whatever. Amiru, Victavi, Evan Johnson, Rodion P. Rodion P. Mel Flygate, Joel Sester, here. David Frost, Andrew Wyatt, Carson Cook, here. Sam Brook, Jamir L. M. Jamir. Wei Chen. Bailey Johnson. Jacob Collins. Morian K. Here. Sunan Santive, Jeremiah Pesca, here. Bill Gilmore, Tim C, Ray Emory, here. Poonam Rani, Jarvin Garcia, here. Cameron N, here. Sanjay K, here. Daniel D, here. Hannah Stanley, here. Nicky Gilbert, here. Belen B, here. Frank San, Frank, Jason Yang, Andrew Gonzalez, James Gay, So this one also only the pen and name. Read the instruction. Jeffrey Beto.
Here.
All right. All right. So this is the meter. Janosh A. Tristan A. Misha Alan Oyami. Faisal A. Faisal?
Yeah.
So you are coming and I didn't hear. Who are you? You are? So why is it difficult for you to say I'm here? Faisal? Abdullah A. Benjamin B.
Here.
Thank you. Rowan Ballinger.
Here.
Emily Becker. Thank you. Jeffrey Beto.
Here.
Sam Brock. Sam. Ivan Burrow. Belen. Victor C. Wei Chen. Anthony Chin. Dwanil Chosky. Cole Coffer. Jacob Collins. Carson Cook.
Here.
Timothy C. Timothy.
Yeah.
Lily Cox. W. Clyde Dye. Cobb Davis. Vita Cavi. David Drost. Daniel Dureka. Gabriel Edwards.
Here.
Michael Gerard. Alex L.
Here.
Thank you. Ray Emory.
Here.
The homework is not due today. Yes, Father. Hannah Frank Family. Mela Flyger.
Here.
Thank you. Jeremy Garcia. Nick Gilbert.
Here.
David Gilmore. Andrew Gonzalez. Russell H. Spencer Hunt. Lee here.
Here.
Lee Hong.
Here.
Who are you? Matthew Hubbard. Evan Johnson.
Here.
Bailey Johnson. Ryan Jones. Sanjay K.
Here.
James Kramer.
Here.
Jordan Kramer. Gerardi Cook. Connor K.
Here.
Morgan K.
Here.
Thank you. Tewo K. Sung Jun Lee, Robert L.
Here.
Thank you. Phuong Ma, Alexander Mason, Ian McBride, Dennis Mezanovic,
Here.
thank you. Alec Moore,
Here.
James Moore, Jay Mullet, Mira Morali, Cameron N,
Here.
Sohail N, William Newcomb, Yijit Onden, Poonam Rani, thank you. Peyton Isha, Daniel Persson, Jeremiah Pesca,
Here.
Kevin Fan,
Here.
Ashley Powell, Radion P, thank you. Elijah R,
Yep.
John Roberts,
Yep.
Amen. Sunant S, Yogi Saputa, Joel Sester,
Here.
Austin Chia, Alexander Shelley, Robert Shaw, Ronnie Song, Huan Chen Su, Frank San,
Here.
thank you. Daniel Trank, Andy Beruca,
Here.
thank you. Millions M, Cody W,
Here.
Amanda Williams, Carissa Wood, Andrew Wyatt,
Here.
Jason Yang,
Here.
Roxanne Zhang, all right, so a number of people email me about homework 3, and a number of people brought it to class today. So this was not yet assigned, has been there since a long time. So you should take a look at. We ran on another schedule because we had a couple of days off because of the snow. And so I write it there when the homework is due, and then we try to catch up. Sounds good enough? Is there any better way to do it, more efficient? Or you just prefer it?
You have a half of random dates.
I'm sorry?
You could have a half of random dates and just randomly pick a date.
Thank you. Any other idea? All right. So today we are going to finish algorithms, and I will write there that next Monday homework 3 is due. Depending how far we go into sequences, I'll assign and counting, I'll assign the next one. Sounds good? All right. Before we continue, is everything all right regarding the organization of the class? Since we are talking about this, like submit the homework. Let me remind you, once your pen name appears on the website, it's there, it's attached to your name, it's not going to change. So you don't have to write it again. Write your name on exams and on homework. Yes?
Right, when is homework 3 due?
So, next Monday, and I'll write it there, so you'll find it there, just for confirmation.
You're not saying that.
I'm sorry.
You're not saying that homework number four will also be due next Monday, are you?
No, I don't think so, because it will be too much, and we are not going to cover all that we need for that. Yes. And if we skip a homework at the end, that's fine. We'll adjust everything. All right. Anything else? So I guess you saw the result of midterm 1 online. I think it should have gone better. I'd be happy to do a couple of problems here, maybe just to show how you go about solving them. So starting with the full term, after long discussion with my colleagues, we decided to simplify the content of this course. So we changed the textbook. Before was a text that was 1,000 pages or close to that, and we have this one which is only 150. And this is much simpler. A few subjects has been taken away. And my sense is that because it's so simple now, people don't take it seriously. And actually, when the exam, the content was bigger and the depth was more, students did better. So I don't have a good explanation why the result is relatively low. Typically, the second midterm students do much better because they take more seriously the preparation. Just a shame that they don't do it the first time. Yes?
I think it's for two reasons.
Yes.
So with all due respect, I think that the textbook for this course is not that good. I've gone through 6 different textbooks.
Yes.
And the best one that I've found that's the most relative is called the Book of Proof. I don't know if you're familiar with it. The Book of Proof is great, but you have to compare with the organization of your class and kind of jump around.
So the content is different.
But you guys,
It's a nice book and I like it.
yeah, in the midsection it is, but I mean it still has an excellent understanding of sets, subsets, and also relations and some function work as well. But I found like a function, what I'm trying to get at is like just the notes being composed how they are in this short condensed section. It's not like, I don't think it's sticking as well as what you might be thinking because it's new material for us.
It's no material. All right. Most of the first midterm wasn't new.
No, I'm saying the book, like this
Yes.
class in general, I mean, assuming you're the same people, so like, we're learning how to do it right now.
Yes. All right.
So I'm just saying that's probably why you expect something.
If you send me an email, I'll be very grateful with a pointer to the book and everything
I
else.
have a bunch of books I can also do that.
All right. Thank you. Yes.
No, I've had more problems with
Oh, sorry. Someone was. But I want to listen to you too. But he was there first. So.
I would just say the material's gotten better from the last time I took the class. You're fine the way we're going to it's less good. But you could just go more problems from the class. Like maybe with midterms or something. Or the midterm or like
Yes.
your problems is like you go through the steps and explain the points, but I think explaining the problem is kind of it makes it tough to understand and better. Makes any sense.
So do more problems in class or assign more homework.
Or maybe
No. This is not a threat. I mean, I think the people should do more problems than the one I assigned. For some ask the question. I'd be happy to take the question. All right.
So, it's kind of similar to you saying, I know I would benefit from some more problems that have solutions that we develop, so we can do them and know we will do right without having to.
All right. Here, I would like some examples. So, if you can send me an email and say, I would benefit from this problem, having the solution. Because I need to
I
understand.
just know, for instance, in most classic textbooks, you can go to the end of the chapter and find dozens of problems with solutions to that develop.
Yes.
So it's helpful to at least have a feeling for that.
I think there is something online about this. And if you look for,
I was looking through some of the other textbooks that you offer. You guys-
so because the author has also a bunch of exercises and homework that we assign with that, which are, I think, much more complicated than the one we do here. So typically I don't send the student that, but thank you.
And kind of relating to that idea, doing a little bit more examples in class, I think that at least this midterm, a lot of the problems were contingent on understanding the rigid definition of something, and I think
Rigid.
yeah, like exactly what a type of relation means or whatnot, and to do specifically counter examples, I think in
Yes.
class, examples where, this relation looks reflexive but it's not, or this might look like a proper subset or something like that, so understanding what doesn't count as a thing.
All right. Thank you. It's useful. You shouldn't look reflective if it's not reflective. So I'm not.
Well, it was like the example.
All right. Yes.
I think what we're getting at is during lecture, like more consistent application, like is helpful there. Like knowing what the symbol means might set that way.
Yes.
And dissecting the problem first.
Yes.
And then going into how to actually construct it. So like you give us a formula and say, here's what it is to construct like deconstruction. Now we'll go through one problem. This is how it's done.
Fantastic. Help me to do this. When you do a problem, suggest how the problem should go. So I do exactly what you asked. Thank you. Yes?
Would it be possible to, after the homework is due, post the solutions?
So the solution, when you get the grade, if your solution was wrong, you should get enough information what was wrong.
It's the check mark. They don't say.
No, check mark if it is correct.
No, I mean, like, if you get it wrong, then.
So they should do it. If they don't, I would like to see it because they are supposed to do it. All right. Yes? Thank you.
Specific to the text, coming into a classroom for the first time in 17 years, I feel this text is very presumptive, that I know some base language that I may have known 17 years ago, but there's very little, like you say, symbols and such, they've changed. So even if I knew them in calculus 17 years ago, there's some symbols that aren't quite matching up to my language. So that, specific to the text, I think almost 1,000-page text might be more beneficial in that context because there's more detail. But otherwise, I like how friendly the text is.
So congratulations for coming after 17 years.
Yes.
With the class with 100 students, one side fits all.
Absolutely.
Doesn't hold.
Absolutely. I'm just,
So-
you were saying this text is smaller now, and
Right.
you had more like before, it might be because it's lacking some definitions.
So for you and everyone else, if you need a special attention, we'll be happy. You can come to office hours, you can go to the PA, don't hesitate, we do it. And there are the tutors, so also the tutors. All right, thank you for the feedback. What I got after all this is maybe to do more examples in class. All right, thank you. All right, so where are we? Algorithms. So let's briefly review this one. what are we discussing? What is here the bird view? We have a difference between an algorithm and a function. When we have a function, we don't care how the result is computed. We just have a definition. The function class adds a two number. How you do it really doesn't matter. If you do pen and paper, you do it in a certain way that you probably learn in first grade. The CPU of a computer does it in a completely different way. When we define addition, we don't care one or the other. When we care how to compute something, we talk about algorithms. Algorithms is a sequence of steps, is a recipe to get the result. Because it's a sequence of steps, and basically we don't know whether we have to do 2 steps or 2 million or 2 billion steps, because depending on the number of steps, we may be able to compute or not. And so we talk about complexity. Complexity is the idea of measuring how difficult it is to compute something. Here there is a key concept that we call a running time. And I said that this is very misleading. So who can tell me what is the running time? Which is not looking at your watch when the computer is getting the solution.
The number of operations you have to do on each input.
Yes?
The time it takes for a program to start the execution.
So why we say that is misleading? I think I said it several times. Yes?
Because the running time is like the number of iterations and doesn't tell you actual.
So the running time is a function. And now we know what is a function. A function is something that takes an input and produces an output. This is the running time. So if you have to tell me what is the running time of some algorithm, I want to see a function. I want to see something that takes an input and gives me an output. So what is the input and what is the output? The input is the size of the problem that you want to solve. And so if you are sorting, the size of the problem is the number of elements that you need to solve. This is very intuitive. The more elements you have, the more you have to work to sort them. I sort your exam because then I have to put them inside the grading system. If I have to sort 50 or if I have to sort 100, makes a tremendous difference. So the size of the input. If you have to multiply two numbers which are not small, which are many digits, is the number of digits. Multiply two numbers that are 100 digits is much simpler than multiply two numbers that are 200 digits. Much simpler. What is the output? The output is how many times some operation of your algorithm is being executed. You pick the operation. Typically, you pick an operation which is representative. An operation that the longer, the more difficult it is to compute the result, the more you execute. And so, if you sort, for example, you have to compare two numbers to know which one comes first. And so, for a sorting, a good measure is how many times you compare two numbers. All right? And so we have this running time, and we want to compare two running times to know whether one is very different from the other or more or less is the same. And when I say different, we want it better, or we may have to realize that it's worse. And so we use this notation, big O. What does it mean that the one function is a big O of another function? So here we have f of n is the big O of g of n, means that f of n grows no faster than g of n. Big O means no faster, no worse, no bigger than that. And how do we express this mathematically? Formally. We say that the absolute value of f of n is less than or equal the absolute value of g of n under a couple of conditions. Is smaller under two conditions. One, that we are allowed to multiply g of n for some constant. This is one condition. The other one, we don't look for any argument of this. We look only for the arguments bigger of some threshold n.
So n is the amount of inputs, right?
N is the, well,
Or the size of.
now we forget this one. In your mind, yes. N is the size of the input. Yes.
And then
When we discuss this one, we don't look at algorithms anymore. We don't look at input, output. This is just, we talk about functions and how they grow.
I guess my question is, so n is just saying you have to perform it at least
M.
m? Yeah, so what is m?
M is that for small values of the argument of f, we don't care. We care in the long run, when the numbers really get bigger.
So m is just like where you're starting to count from for your size.
Where it's becoming interesting. Yes?
So can you have different f of n, big notation functions for different values of n, like if you start from 0 as opposed to if you start from 1,000?
So I'm not sure I get the question, but let's do an example and then you ask me on the example. So I didn't want to redo the lecture on this. So let's take a function 2n plus 1. This is a function. Think about this as f of n. All right? So here I want to know if f of n is O of n. So n is equal g of n. All right? So if f of n is is O of n, I know that 2n plus 1 grows no faster than n. Of course, 2n plus 1, if n say is 10, is 201. No, it's 21, sorry. And so this is bigger than n. Are you with me? So, for n equal 10, f of n is 21, and g of n is 10. So f of n is bigger than g of n. But we want to say that f of n is smaller than this under those two conditions, right? So let's see what are the conditions. Who can help me finding C and M? How do we find it? We say 2n plus 1 is less than or equal to n plus n for n greater than or equal to 1. You with me? So this is less than or equal 3n. It's the same. So what do I have? I have that the absolute value of f of n is less than or equal C, absolute value of g of n for n greater than 1, and C, this one I make it a 3. So this is my C and this is my M. And so I prove what? I prove that f of n is O of n. All right? Is this example good enough to explain? Yes?
Are there functions that are in O of n and then also in theta, in omega event, but then not in theta event?
All right, so let me postpone this a second because I think you are quite ahead of most other people here. Then I'll answer your question. Yes?
So I think in the previous lecture you misunderstood the purposes of C and M in
Yes.
the definition. In homework or in the test, Luigi provided an f of n as well as a set value for C and M, or are C and M just tools we use to determine if any value of C and M satisfies the formula, then you know the big notation.
So I don't know what I'm going to put in the exam. We can look at the homework. But why don't you send me a couple of examples of this? The way you think it could be phrased.
So like if you're let's say you're
Let's take this offline because so you can think a little bit more about this. Yes?
So I understand the progression from like 2 and 2 and what's in
Yeah.
3. Is there like a process to this that's not just using the intuition of 3n is bigger than 2n plus 1? Like, is there like a mental algorithm you can go to get there versus?
So the way I do it is that I change the constant into n. Because I have on the other side, I have O of n. So I have to compare with n.
Yeah.
So I have to get rid of the constant. And so I change the constant into n. If I had to compare with n squared, probably I would change the constant with an n squared or something like that.
I just feel like getting to 3n, you're just stepping up.
Right, I don't have any algorithm for doing this. I don't know any algorithm for doing this except massaging a little bit to get the result. Yes?
I guess what we're saying is that how do you know within what limit you can massage it?
There are no limits except logical interest. So the limit is that you cannot say 2 plus 2 is equal 5 and then show something. But if you say 2 plus 2 is equal 4 and then you get the result, then that's fine. All right, so I think before I got a question and now I'm trying to answer it. You want to ask me your question again? Yes?
Yeah. Are there functions that are in big O notation or big omega notation, but then don't have an equivalent for big theta? It looks like big theta has their own.
So, the intuition is that the big theta is a conjunction of a big O and big omega.
But we're only, my intuition says that only works for functions where it describes both the lower and upper bounds. in
So,
one function.
look, we can say that n, let me write it here, n is O of n, right?
Yep.
N is omega of n,
Yeah.
and n is theta of n.
Yeah. But what
So
if-
there is a function that is in all of them.
But a function like let's pretend we're traversing a graph to find a certain value.
All right.
Theta, big O notation is looking through the entire list. So then we have different.
O
maps
is,
rolling
when
back.
you say looking for the entire list, you are thinking about some algorithm. These are functions. So
No, but is there like an algorithm or a function that wouldn't have the same O and theta, so then it wouldn't be the same omega, O and omega, so it wouldn't have the same theta? Like this happens for we have n, and n. But it
well,
just-
but I could put here 2n. I don't know.
But would it be like n squared, n cubed, what would be the last one? Does that make sense?
So I don't have well the parameters of the problem. You are looking for a function f of n that let me write it here if I can answer. You want f of n to be O of
O of like n squared.
n squared.
Sure.
And then you want f of n to be what?
Omega n, right? So that's the lower bound.
So,
Yes.
so this, you don't find this f. I don't think you find this f. Because f of n has to be smaller than n squared in the long run, and bigger than n in the long run. So there is no such function.
N squared is exponential, and n is linear.
Right, and big O has to be less than n squared and greater than n. All right, so this is n squared, this is n, and you are looking for a function here?
Yes.
All right.
Can we write that in big theta notation?
Can we write this in big theta notation? No.
No. Okay, that's exactly what's out.
All right. All right, so let me briefly finish this. So once we understand the big O, it's very easy to understand that big omega and big theta. Big O means that the function grows no faster. Big omega, that the function grows no slower than the other. A big theta means no faster and no slower, which means more or less the same. Why do I want to qualify this more or less, which is not very mathematical? Because we have those two conditions, C and M. So grows the same if you factor in those C and M. If I speak freely to give you an intuition, I say more or less. All right, so after this we look at some algorithms. One was the greatest common divisor algorithm. We did it. A few examples. Should I make another example? They're all the same.
I was just wondering if you could just go through like a quick example of showing the 2n plus 1 example before.
The 2n plus 1.
Like the example you did before for big O, where 2n plus 1 is O of n.
Yes.
You could go over an example of if that would be theta of n.
Theta.
Yeah, like is 2n plus, if f of n equals 2n plus 1,
All right. So
would that be theta of n? Would there be the example?
So you would like to see that 2n plus 1 is theta of n. Right? So what do we have to prove here? We have to prove, let's say n greater than 0 to begin with. So we get rid of the absolute value, is a little bit easier to read. Good enough? We can pick n greater than n, so we start with a guess for n which is 0. Then we can even make it bigger. So we want to show that this one is less than or equal C1n and less than or equal C2n. All right? To prove this one. You with me? All right. So we found already out that this one is 3, right? Can you make any guess for C1? 2 is good. Can you make an even better guess? 1. So we don't have to do anything. All right? Did I answer your question? All right. So should we make one more example of the greatest common divisor, or everyone is comfortable with that? I'm sorry? One more example. You want to pick 2 numbers? I'm sorry? 312. All right. So we want to find the greatest common divisor of 312. All right? So we write 300 is equal 12 times something plus something. What are these two numbers?
Q and R.
Say it again.
Q and R.
Yes, what are the numbers?
Quotient remainder.
You didn't understand. I cannot do this in my head. Has someone a pocket calculator there? Maybe on their... I'm sorry? 25 and 0. You're good. All right. It's really 25. Yes. All right. So this probably was a somewhat a degenerate example, right? And so we found it. What is the greatest common divisor? 12. Yes? That is not so degenerate.
301.
301 and 12. Someone said 300. You pick the number. I'm happy to do it with any number. They are all the same. All right. 301 and 12. What is? 25 plus 1, right? So now what I do here? 12 and 1. And this one is 12 plus 0, right? And so the greatest common divisor is this one. All right. So it really doesn't make any difference what the number. Here there is the algorithm. Here there is, in these two lines, there is the algorithm that says if the second is 0, it's the first. And if the second is not 0, what do? You replace the first with the second, and the second with the remainder of the division of the first by the second. And so this is a more interesting example because you do a number of steps until finally you get to the result. All right. Then we discuss encryption. You have a way more complicated encryption algorithm, certainly a much better one in the textbook, but we replace this with a simpler one because as far as algorithms are concerned, the difficulty or the understanding is the same. And so we represent the letters with the numbers between 0 and 25, the 26 letters. And the encryption says, look, we pick a letter, multiply by A, add B, and consider mod 26, because we go from 0 to 25. And we wanted this to be a bijection. So we encrypt, and when we decrypt, we come back exactly what we had. So how do we pick A and B? We said, we pick A so that the greatest common divisor of A and N is 1. And so here we have an example, I don't have to do 1. F of x, I do mod 5. If I take 4x plus 1, this is a bijection. Why is it a bijection? Because the greatest common divisor of 5 and 4 is 1. All right? So I think we did some examples with the spreadsheet. Let me do it again because for the new material I need it. Spreadsheet. So let me, instead of doing it with a 26 letter that gets too big to manage and see here, I do with a number between 0 and 9. And here I do All right, let me make this a little bit bigger. All right, so here I have mod this one, say times 4 plus 1, mod 10, which is the example in the book, except that in the book is mod 5 and here is mod 10. Is this a bijection? No. Why not? Because 0 and 5 goes both to 1, so it's not injected, and so it's not bijected. Alright? What is the explanation? Why this is not a bijection, according to the theorem we just looked at? Fantastic. The greatest common divisor of 4 and 10 is not 1, is 2. So, here, what should I pick for the coefficient A? 3, for example. 3 will work well. All right, this is a bijection. And so this theorem says, look, if you do this form of encryption, if the greatest common divisor of A and N is 1, is a bijection. So if you encrypt it this way, how do you decrypt? So you decrypt in the same way, in the sense that the decryption is x times something plus something mod n as before. So we have to find this k and this c. And here is the rule. C is the one that the encryption sends to 0. So, if you look at this one, what is the C? 3. I'll mark it here so I remember. What is K? It says K, if you multiply A by K and you add N by M for some K and M and you get 1, you have the value that you are looking for. So let me write this on my piece of paper here. A, we pick a 3 times K plus N is 10 times M, this is N. Here I want 1, of course, mod 10, everything mod 10. So who can tell me what is K and what is N? Minus 3 and 1, this becomes minus 9 plus 10 is equal 1. Very good. So we don't have the negative. We only go from 0 to 9. So what is this 3 mod 10? Negative 3. 7, very good. So now if I do this, if I do mod this one, yes, thank you, this one, star 7 plus 3 mod 10, the first function is the encryption from the first column to the second. The second is the decryption. And so when you compose both, you get the identity. So 9 goes to 9, 8 goes to 8, 7 to 7, and so on. Okay, so yes?
Which letter is the 7? Is that the A, the K, the N, or the 7?
The K.
Okay.
Yes. Let's go back to this one. And is here. Says the decryption is kx plus c, where c is the one that the encryption maps to 0. And k satisfy together with m this equation. If A and N, the greatest common divisor is 1, you are guaranteed that this always exists, that will give you the greatest common divisor 1.
And then what was C?
C is the one that is mapped to 0. Encryption of C gives you 0. So if we look at this one, the encryption of 3 will give you 0. So is this example good enough? We can make another one, but it's exactly the same. If we want encryption, the greatest common divisor of 8 and 10 has to be 1. So we have to pick a number which is not even and which is not 5. All right? For the decryption, we have to look at which one here goes to 0, and then we have to find that k by solving that equation. Typically, for numbers so small, it's very easy to solve the equation. So I need some feedback. When I know whether you need to see another example or this one is good enough, or you want to do one yourself rather than seeing from me. Yes?
I'm just still not totally understanding
Yes.
the values for the variables for your decryption function.
Yes.
So, because you have a k x plus c mod n,
Yes.
your n is still 10.
N is
your,
still 10.
Your k is now 7.
K is now is 7.
And your n, and your x is your 1, 2, 3, 4, 5.
Right, so it's whatever is the input of the function.
And now what's your c is 4?
C, in this case here,
Yeah.
C is this 3, because when you encrypt 3, you get a 0. C is the one that when you apply the function will give you 0.
So your c is now just your x?
C is the input of your function that will give you 0. This is a function. From this column to this column is a function.
Yeah.
So you pick the element such that the image of this element is 0. This is your C.
And it will always be
Whichever goes to 0. So this is not a strong encryption. Why? Because the A and the B that you pick to do the encryption, they are in a very small space. When you have the 26 letter A, there are a dozen of possible values. B, there are 26. So you do 400 or 500 attempts, or whatever is the number, and you check all of them. It takes a millisecond with the computer. So other ways to do it, instead of consider one letter and encrypt it, you can consider two letters, one near the other. And so instead of mod 26, you have mod 26 squared. And it's just slightly more difficult. You can consider 3 letters, 4 letters, or 1,000 letters. If you consider 1,000 letters, it's not very easy to break. Not very easy. However, if you consider 1,000 letters, you run into a problem.
Before you change, can you show again the 4 minutes?
Yes. This one is the input times 7 plus 3. There is a spreadsheet in the material online here that shows all this in great details. If you come here, shows how you encrypt this one, how to decrypt it. You can play a little bit. So we have a final point, which is this fixed point. First, let me tell you what is the fixed point and the problem, and then we find a solution for this. a fixed point for a function is an argument such that when you apply the function, you get back the same argument that you have. So, let me change this a little bit. Instead of doing this plus 1, I do this plus 4. Oops. All right. Now this is broken, but I'm going to fix it soon. But first, I want to show you. Here we have a function, right? Is this a bijection?
No.
Why not? Yes, it's a bijection. Right. Should we find the decryption? So this is another example. So let me do it here first. So this one is 3x plus 4. All right, mod 10. Thank you. So how do I find the inverse? The inverse will be kx plus c. What is this c? Let me go back here. C is 2. Why is 2? Because f of 2 is 0. So this will be 2. What is k? Here I want what is k? We have k times 3 plus n times m is equal to what? 1. This is exactly the same I had before, right? So k is exactly the same as I had before. So to compute the inverse now, here I just need a 2 rather than a 3, right? And so I have the inverse. Oh, you didn't see it. Sorry. No one complained. Maybe you were doing it yourself. So this one here is the input times 7 plus 2. So here something interesting happens. When you encrypt 8, you get 8. And actually, if you look also, when you encrypt 3, you get a 3. So now suppose that rather than having these 10 values, each one of these is a block of 1,000 characters. Let's say 1,024 because this is a disk sector. So we encrypt the disk sectors one after another. What is going to happen if you have a fixed point? Right. So you have this long document which is all impossible to read, but once in a while you have one page which is exactly what you had at the beginning. Terrible. Right? Yes?
Are these fixed points, you know, the kind of severity of how much it matters depends on the size of what you're encrypting? If it's like a single character, then you can't really tell if it's the same as its decrypted version.
Right. If you do it one character at a time, it doesn't help you very much.
Right.
But if you do 1,000 characters at a time, those 1,000 characters are exactly without the encryption. And so we want to avoid the fixed points, right? Because of this reason. And so we have a theorem that saves us. Here it says, look, if the greatest greatest common divisor of a minus 1 and n does not divide b, then there are no fixed points. So if the greatest common divisor of a minus 1 and n does not divide b, there are no fixed points. So here, because we have a fixed point, we are going to see that the greatest common divisor of a minus 1 and n divides b. Let's look at this. Here, a is 3, right? So what is a minus 1? 2. What is the greatest common divisor of 2 and 10? 2. And so 2 divides 4. And so we must have some fixed point. And so when we pick A and B, we have to make sure that there are no fixed points. Here in this example that I do later, and I challenge you to break the encryption. So here there are a couple of fixed points. It's not that when you see, if you look at this way, you have no idea what I'm writing here, right? But there are a couple of fixed points. Someone had a question? Yes?
There's a question on board 3 that is about fixed points, and it's asking you to find the fixed point. So the fixed point is just A. The A for which A minus 1, GCD A minus 1.
The fixed point is an input of the function that the function transforms the input in the itself.
Okay, so it's not the A, it's the X.
Is the x for which f of x is equal x. This is the fixed point. All right. Enough about encryption. Should we take a break? All right.